resonance structures. And I'd like to continue with that idea today. We'll use this as a platform to really start thinking like organic chemists. One of the things we'll see here, and as I said throughout the course, is the use of curved arrows to represent the flow of electrons and to help us think about different molecular structures. Later on, I'll be using these in the discussion of reactivity as a fundamental way of thinking about reactivity. Now, the structures, I've just repeated the last panel of the blackboard that I drew last time. And the structures that I've drawn there are probably not the way you would see an organic chemist draw the structures. In fact, for me, it was very hard to discipline myself to actually draw out all of those atoms and bonds, because for the most part, this is not how organic chemists think. We tend to focus on parts of the molecule and fill in the rest. Let me show you, for example. So remember, this was acetate anion on the top and benzene on the bottom. Let me show you how an organic chemist would typically draw these. And as you go along, you're going to get more and more used to seeing these types of structures. What you would probably see is called a skeletal structure. In skeletal structures, you represent carbons just by the angles formed by lines, and implicit then the hydrogens are simply filling in the extra valency. Let me show you what I mean. If I were in a rush, probably unless I were focusing on a particular part of the molecule, for benzene, I would write this structure. Now, implicit in this is the same information that's explicit in this structure here. In other words, implicit in this structure is at this junction, there's a carbon atom. Because we have three valencies filled by bonds to carbon, a double bond on the right and a single bond on the left, we have a hydrogen in this position. In other words, implicit in this structure, and also another legitimate way of writing the structure would be something like so. And it's important to get in the habit of being able to read these structures and really think about them. As we go on to reactivity, sometimes what I will do is to simply focus, give more detail on the parts of the molecule where something is happening and less on other parts. Let me show you a couple of other structures. If I were scratching out the structure of acetate in a skeletal structure, I would write something like this. There was a good question on the Facebook page. Person asked, well, why aren't people showing formal charges, or why are they showing formal charges? Certainly, if there's a net charge in the molecule, you better show it. If there are formal charges in the molecule, the structure is probably sort of correct without them, but generally it's good form to actually write the formal charges. If I'm interested in some detail, you might also see the structure written with lone pairs of electrons, particularly if I'm focusing on reactivity. And almost interchangeably, you'd see an organic chemist write the structure with a CH3 group shown explicitly. So these are all legitimate ways of writing the structure. And these are much more typical of what you're going to see an organic chemist doing than the sort of structures on the left-hand blackboard. You'll be getting more and more of this, and you'll get used to it. It's not a big deal. Let me show you one other compound. Let me show you the chemical compound pentane. Just about any organic chemist would probably write this structure as a zigzag line containing 5 bonds, meaning you have a carbon here, carbon here, carbon here, and a carbon here, and a carbon here. Now remember, since we have one bond to carbon, this group here has 3 hydrogens, so it's a CH3. Here you have 2 bonds to carbon, so it's a CH2. In other words, you might also see it written out, or think of it as CH3, CH2, 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 CH3. What you probably would not see would be this sort of full atom structure. I think you'd find it would get very tedious to write, as would I. Where here's a full Lewis structure of pentane with all of the electron pairs and bonds being written as lines. Thoughts or questions? When you're saying when you don't show bonds?
When you don't show, like, the first example?
First example. Okay. So how would one know if this structure had a hydrogen or a lone pair? And this is why being able to be fluid about counting up charges is so important. Most organic well, first of all, you would always show, okay. Implicit in this is carbon has 4 things bound to it, 4 valencies. If we go back on the periodic, if we go across the periodic table, nitrogen has 3, oxygen has 2. So for example, if I were to write this structure, which is the structure of butanol, where oxygen is in place, implicit in this structure is that there are 2 lone pairs on the oxygen, not 2 hydrogen atoms. If I showed a second hydrogen atom, we'd have a charge on there, and I would show that. So I'll show you a structure like that in a moment. But carbons are where chemists cut corners the most because it's convenient. And honestly, and this is what I was saying about reactivity, if there's a point in the molecule where you're trying to be very explicit, write in the hydrogens. Just don't write them in everywhere. So there is indeed something called a phenylanion, where there is a lone pair and a negative charge at one of these positions. But then I would very explicitly write it in, showing both the lone pair and the negative charge, because otherwise everyone would think, and I would indeed be indicating, that I had benzene, not the phenylanion. Other questions? These are good.
Can you go over the methyl azide example?
The methyl azide example. I will actually not go over that here, but you're welcome to catch me afterward. Or so I gave at the very end, I think I tossed out and said, let's talk about methyl azide as a Lewis structure. I'm going to, in next week's discussion section, throw out some problems very similar to that. Maybe I'll even toss methyl azide in there to get you practicing and thinking about writing these structures. And indeed, if you haven't seen them before, it's confusing, and that's why we practice. So I will either, you can catch me, or I will put that in the discussion section problem. All right, let's talk a little bit also for organic chemists thinking about various forms of arrows. And we've already seen the sorts of double-headed arrows that we use to indicate that these 2 structures are resonance structures. And I made the point last time. This means it's not one, it's not the other, it's not oscillating between them, it's both at the same time, all the time. There's another type of arrow that helps us think, and that's called a curved arrow. And as I said before, this is central to organic chemists thinking. represent, we think about, we help conceptualize how electrons flow, either in converting between two resonance structures, which, as I said, are both at the same time, or in a chemical reaction where you are going from one thing at one time to one thing at another time. Let me show you what I mean. I'll start with our acetate anion written as a skeletal structure. So here is one resonance form of the acetate anion. And if I want to think about how to get to the other resonance form, I can just imagine one pair of electrons on this oxygen, one lone pair, flowing into the carbon-oxygen single bond. That's going to make a double bond. If you imagine going halfway, if you imagine moving those electrons, we can't stop at that point because now you'd have two pairs of electrons here between the carbon and the lower oxygen, two pairs of electrons here between the carbon and the upper oxygen, and another pair of electrons in the bond from carbon to carbon. In other words, we have 10 electrons around this carbon. We can't do that. So we have to push two of the electrons onto oxygen. And again, I use a curved arrow to help conceptualize, to represent that process. And when we're done now, what this means is we've gone to a structure in which we now have a single bond to the upper oxygen, 8 electrons around it, 3 lone pairs, and a bond. We have a negative charge on that oxygen. In the bond to the lower oxygen now, we have a double bond. We have 2 lone pairs on that oxygen. And of course, these are just the 2 resonance structures, not one, not the other, but both at the same time. Let's try that same thought process to envision the interconversion of the 2 resonance structures of benzene. And again, I'm going to use the skeletal structures. Get us thinking like organic chemists. Actually, I'm going to make this a little bit bigger, just because otherwise my curved arrows are going to be crunched for those in the back. So here's a big benzene. So if we imagine moving this double bond, the pair of electrons making up this double bond, over between the 2 carbons on the right. We can't stop at that point because, of course, remember there's a hydrogen here, so that would put 10 electrons around this carbon, and this one would still be fine, so we'd have 10 electrons around this carbon, so we have to push onward here. Push onward here, and when all is said and done, we've moved this pair of electrons making up the double bond here, this pair making up the double bond over to here, and this pair making up the double bond here, and that takes us to the other resonance structure. And once again, it's not one, it's not the other, it's both at the same time. Oh, great question. Do the arrows always have to be clockwise? No, it is perfectly as right to write them counterclockwise here. Other good questions. Wouldn't it be easiest draw a circle inside. So, like this. You will see benzene written this way sometimes. At this point in your education, the answer is no. And the reason I'm going to say no is at this point, you don't yet have a good enough grasp. We barely talked about skeletal structures. Most people are trying to wrap their heads around the CH2 here. If we do anything not to show bonds explicitly, you will be hobbled. So at this point in your education, I'm going to say no to this. And at this point in your education, for a very similar reason, I'm going to say no to this because most people have trouble figuring out what does this mean, where are the electrons, where are the charges. I don't even know how many electrons are in this structure. So stay away from this. Now the good news is often when we're thinking about molecules, we don't have to write every resonance structure. When I write the acetate anion, unless I'm talking about resonance structures, I'm going to pick one resonance structure. The two are equivalent. They're identical, except that they have the double bond on the top or the bottom. I'm going to pick one, write it, and show its reactivity. So the good news is you often can get away with one, but you need to keep this extra information in the back of your head that there's another resonance structure. Other good questions? They do it like that. Stay away from it. By the way, for people who are inquiring, when I'm focusing on this, I will probably say, write a structure of such and such, or write all important resonance structures of such and such. Show all bonds, all lone pairs of electrons, all formal charges. So I will make it very clear to you. But honestly, you will get yourself in trouble. And particularly thinking about 12 electrons, you will have trouble with that. Other good questions?
Does the second bond and the double bond pair have to be on the inside of the ring?
Another good question on form. Doesn't have to be on the inside. It's certainly traditional. You will see some people will write benzene. You may see it written like this, where it goes like this. I would say out of tradition it is. There is a molecule called benzene that has a triple bond, and most people would write the third bond over here. Out of convention, I'd say most people would look at you funny if you wrote it in any other way. All right, let's talk. We've been talking about resonance structures, and so far the resonance structures that we've talked about here today are equivalent resonance structures. It's 50% one, 50% of the other. Let's talk about non-equivalent resonance structures and see some rules for which is more important. So last time I drew the molecule formaldehyde to get us thinking about organic chemicals and about bond dipoles and molecular dipoles. I'm going to redraw the molecule formaldehyde. And I'd like you for a moment to imagine, put a proton onto this oxygen atom, we're going to be seeing this concept, and indeed using curved arrow notation to help express it in Chapter 2 when we start to talk about Lewis acid, Lewis base reactions. This is the very first beginning of organic chemical reactions, and it also ties into G-Chem. But for now, I just want you to grant me this structure in which, as a thought exercise, I've put a proton onto the oxygen atom. That puts a positive formal charge on the oxygen, and indeed protonated formaldehyde has a positive charge on it. There's a second resonance structure that I can write. Second resonance structure in which now our positive charge is on carbon. And you notice this is a great example for me to be drawing things out explicitly, for me to be drawing in the hydrogen atoms, because otherwise most of us would become confused if I just drew a carbon there, just drew a line on how many hydrogens are attached. So let's take a look at these resonance structures and think about what's good and what's bad about each of them. What's good about the structure on the left? The resonance structure on the left. Double bond. What else? Not the formaldehyde. So what's good about this structure? Fills the octet rule. Bingo! The structure on the left fills the octet rule. I'll say fulfills octet rule. And the structure on the right? You're shaking your head. The carbon doesn't have a complete octet. What's bad about the structure on the left? Positive charge on oxygen. Why do we like a positive charge on oxygen? Because oxygen is more electronegative. So this is good, bad, positive charge. All right. So now I want to address the question, which is more important? And if we want to think about resonance structures, the first and foremost rule is filling the octet rule, that every element in the second row, every element in the row of carbon gets a complete octet. So this is the most important factor, and I would describe this resonance structure as the major resonance structure and this one as the minor resonance structure. In other words, if I wanted a picture of acetate anions, both of those structures contribute 50-50. They're both equal. They're both equally important. If I want to picture a protonated formaldehyde, this one contributes mostly to the structure. In terms of most, I mean like 90+%. I'll give you an example in just a moment, a sister molecule, where we can actually see just how big this effect is, where I have some experimental data to show you. And what I want to talk about now, which will lead us up to this, is bond length in organic chemistry. And it's worth having some numbers at your fingertips and being able to use them to think about structure and bonding. I'm going to show you some numbers and some trends, and then come back to a sister of our protonated formaldehyde to explore the implications. All right, so bond lengths. Distance between atoms, length of a bond, is typically measured in angstroms. Bonds are on the order of 1 or 2 angstroms in length. An angstrom is 1/10 of a nanometer. It's 10 to the minus 10 meters in length, obviously very small. Up until recently, nobody's really seen molecules. Now there are microscopic techniques where people can actually see molecules. And there was just a paper in the journal Science that was incredible. It also made the New York Times Science section, where they used a tiny little tip on an atomic force microscope with a single carbon monoxide molecule bound to the tip to rasterize over a molecule of pentacene. That's a molecule with 5 benzene rings connected to each other, all side by side, 5 rings in a row. And they could see the shape of the molecule, they could see dimples in the center of the molecule. It was incredible. We are in a new world in terms of being able to understand and actually see molecules. So they're basically feeling their way across. These are really, really tiny sizes. All right, for calibration, a carbon-hydrogen bond is about 1.1 angstroms in length. At the end of the class, somebody asked me, what's this little thing? It's a tilde. It's approximately Ca, if you want, circa. How about carbon-carbon bond lengths? These are numbers that are worth having at your fingertips. A typical carbon-carbon single bond is about 1.54 angstroms. A typical carbon-carbon double bond is about 1.34 angstroms. And just to complete the entire set, a typical carbon-carbon triple bond is about 1.20 angstroms. Oops, I drew 2 tildes here. What am I doing? All right. Now, why do these facts and figures matter? Well, let's take our molecule benzene here. All of the bonds in benzene all of the carbon-carbon bonds in benzene are the same length. Anyone want to hazard, want to get a guess of what that length might be? Somewhere in the middle, 1.40. Benzene, 1.40 angstroms. So not as short as a double bond, not as long as a single bond, but somewhere in the middle Not quite halfway, roughly halfway between the two. And we're going to see in a moment, we'll come back to a molecule very close to protonated formaldehyde and see some trends there. Okay, so one thing that comes out is multiple bonds are shorter. So if you want to say bond length decreases with increasing bond order, that's just a fancy way of saying two bonds are, a double bond is shorter than a single bond, a triple bond is shorter than a double bond, and a bond that's 1.5, as we are in benzene, is somewhere in between. Let's take a look at two other periodic trends. Let's move down the periodic table. So we've talked before, when we talked about electronegativity, we talked about there are up-down trends in columns and there are cross trends in rows. What do you think happens as you move down the periodic table, as you move from a bond, say, between carbon and fluorine to a bond between carbon and chlorine, bond between carbon and bromine, bond between carbon and iodine? Longer, indeed. Iodine is bigger. You've got a bigger electron cloud. So I'll say bond length increases as you move down the periodic table. This is what I love about organic chemistry. So much stuff just makes sense. All right, so I'll give you some numbers. Maybe you wouldn't know the exact numbers here because we're getting a lot of numbers here. These are practically good numbers to know about carbon-carbon bonds. All right, a carbon-fluorine bond is about 1.40 angstroms. Carbon-chlorine bond is about 1.79 angstroms. Carbon-bromine bond is about 1.97 angstroms. And the carbon-iodine bond is about 2.16 angstroms. If you look at the length of a carbon-carbon single bond and a carbon-fluorine single bond, you can already see the last trend that I want to mention, and that says as you move across the periodic table. What happens as you move across the periodic table? decreases. So the carbon-fluorine bond, remember, look at the periodic table. Fluorine is across in the same row from carbon. We're not going to move down and across. We're only going to go in one direction, because when you start comparing opposing trends, it's going to have factors fighting each other. As you move across from carbon-carbon to carbon-fluorine, the bond length is shorter, and so you can guess that a carbon-nitrogen bond is going to be a little bit shorter than a carbon-carbon bond, and a carbon-oxygen bond will be a little shorter than that. Carbon-carbon single bond, about 1.54 angstroms. Carbon-nitrogen single bond, about 1.47 angstroms. Carbon-oxygen single bond, about 1.43 angstroms. And carbon-fluorine bond, 1.40 angstroms.
What is a carbon bond with a noble gas in the section?
Ah! Oh, I love that question. What about a carbon bond with a noble gas? Well, you're not going to... Neon has never been characterized bonded to top count. So carbon-xenon bonds and carbon-krypton bonds are known. I don't know the length of a carbon-xenon bond relative to a carbon-iodine bond, but I wouldn't be surprised if it's actually longer rather than shorter. It's a great question. Now, why is it getting shorter? Electronegativity. Electronegativity means what? Or why does this make it shorter?
Because you've got the negative electrons attracting the positive protons in the other atom. So the smaller the atom, the closer the electron can get to the proton on the opposite atom.
You have the negative electrons attracting to the positive protons. So in fluorine, there are more protons. They're getting pulled, the electrons are getting pulled in tighter, that's what you're saying, and hence the bond is shorter. Exactly. And the one downside I dislike about the short answer of electronegativity is it's sort of the phenomenological, explaining the phenomenological. And then when you scratch below the surface and start to get to nuclear charge, we really get to the explanation. So the electronegativity is the shorthand. And then the longhand is those extra positive charges want the electrons more. All right, let's take a look at some of these numbers here. And I want to keep, I guess, this blackboard up and these trends up here. So I'm going to take the right-hand blackboard. So remember when we discussed protonated formaldehyde, I said the resonance structure with everyone having complete octets is more important than the resonance structure in which the positive charge is on the carbon, but the carbon doesn't have a complete octet. That's really the most important thing to understand in writing resonance structures. Let's take our understanding of bond length and bond order now and take an example of this where I have some data. And I'm going to draw another structure. I'll draw it let me draw it. Okay, oh, all right, I will draw it sideways. This is, of course, the same type of structure that I drew for formaldehyde. But I'm just drawing it sideways just because I want to focus on bond lengths. All right, this molecule here is called methylene imine. We're seeing a lot of weird molecules, but it's also helping us get used to writing the structures of organic compounds. All right, so it's the cousin of formaldehyde because nitrogen is very similar in some ways to oxygen, except with one more valence. All right, let us imagine now a couple of other molecules for comparison. So the carbon-nitrogen double bond, we haven't discussed it over here, but we know it should be shorter than a carbon-nitrogen single bond. The carbon-nitrogen double bond in this molecule is 1.27 angstroms in length. And I'm going to compare that to a molecule with a carbon-nitrogen single bond. We should already know the bond length. This molecule is called methylamine. The carbon-nitrogen bond length is 1.47 angstroms. Now, let's consider the protonated analog of methylene imine, the methylene iminium ion. So just as in formaldehyde, I said, imagine for a moment, putting a proton on the lone pair of electrons of the oxygen in formaldehyde. Here I'm saying, imagine for a moment putting a proton on the lone pair of electrons on methylene imine. Now, the length of the carbon-nitrogen bond in methylene iminium ion, let me write out the name. The length of the carbon-nitrogen bond is 1.29 angstroms. In other words, that carbon-nitrogen bond is a little bit longer than a carbon-nitrogen double bond, but a lot shorter than a carbon-nitrogen single bond. Let's think about the two resonance structures that we could write for the methylene iminium ion. One resonance structure with a double bond to nitrogen and a positive charge on the nitrogen. The second resonance structure with a positive charge on carbon and an incomplete octet. This resonance structure, you'd expect to have double bond character. This resonance structure, you'd expect to have single bond character. And we're a lot closer to a double bond than to a single bond in length. In other words, again, we see that the major resonance structure, the most important one, the one that contributes roughly 90% to the picture of the methylene iminium ion, is the one with the complete octet. The minor resonance structure still contributes a little bit, but not a whole heck of a lot. The reason that I don't forget about the minor resonance structure is as we go on to talk about reactivity and as you progress through the course, you will see that often the minor resonance structures help you think about where things with electrons, molecules called nucleophiles, where they come and form bonds. We'll take one last example. Take an example of the trifluoromethyl cation. CF3 plus. It's a carbon with 3 fluorines bound to it and a positive charge. All the CF bonds are 1.27 angstroms. And remember, we said that a carbon-fluorine single bond is about 1.40 angstroms in length. So we have very little single bond character. Let's see if we can write some resonance structures that represent the structure of the molecule. And if I put together all of my atoms and a positive charge on it, and each of the other fluorines has 3 lone pairs and a single bond to it, I can write 2 other resonance structures just like this, except where I have double bonds to the other fluorine. One where I have double bonds to the fluorine on the right, and another where I have a double bond to the fluorine on the left. And I realize things are a little bit cramped on this blackboard. So a single bond to the fluorine on the right, double bond to the fluorine on the left, and a positive charge on it. And together, these 4 resonance structures make up a picture of the trifluoromethyl cation. These 3 resonance structures on the right, which give a complete octet to carbon, all are consistent with the short bond length between carbon and fluorine. Collectively, they are the 3 major equivalent resonance structures. And the structure on the left, just as we've seen with the methylene iminium ion, is a minor resonance structure. well, I think this is what I'd like to say about resonance structures. Next time, we're going to pick up with a discussion of structure and bonding through a molecular orbital approach. And this will lead us to